This topic is related to the Maxwell's equation, how this behaves in matter and any material. So the title is Maxwell's equation and matter. I have written this that the Maxwell's equation can be modified when we are working with materials. For a free space, we know about this. If there are some charge in a free space, then the Maxwell's equation we have already discussed. What will happen when we apply the Maxwell's equation for a material? Then we should know about the previous knowledge. Means we know from the previous knowledge when the charge are at rest, then charge and current densities must be. We know about the from the previous knowledge. We have explained this in chapter number 5, chapter number 5 and 6, the bound, the surface charge density, bound surface charge density. This is equal to the polarization, and the bound volume charge density. This is the divergence of polarization. Similarly, we also know about the surface bound surface current density and the volume current density. So how, if we say that this is the bound current, so what it means by bound current? The bound current density must come from the spin of the electron or orbital motion of the electron. But at these bound charges not move from one point to another point. Consider this cylindrical shape. This is some cylindrical shape, and here we have some positive charges, there are some negative charges, and there are some positive charges, and there is some polarization between these charges. If I consider this is sigma b plus sigma b, then this must be minus sigma b, bound surface charge density, minus surface charge density, and plus surface charge density. And if I consider this area dA perpendicular, and if these charges start some motion from here to here, in this polarization, then we can get the current, and the change in this current must be equal to the rate of change of bound surface current density and with some surface perpendicular to this surface. Then this di will be equal to p dot n divided by t and dA perpendicular. And further, this di divided by dA perpendicular, which is equal to partial p divided by partial t if we remove the dot product. Then what it means? Current per unit area. Current per unit area, this is equal to change in polarization. There is some polarization between these charges, and if the current per unit area, if there are some changes in polarization with time, partial p divided by partial t, it means that the polarization changes with time. Then if the polarization change with time, it means that the charges will flow from here to here, and we can get some current. And this current is known as the current generated due to polarization, and we may call this Jp. And further, this Jp is equal to partial P divided by partial T. Here, this Jp, this current, this is known as polarization current. Polarization current. This polarization current is different from bound current, JB. JB is bound current and JP is polarization current. And these are different with each other. How? Actually, JB, this current involves spin and orbital motion of electron. But Jp, this current is different, results which a result of linear motion of charge when polarization changes. If we have this polarization current, then the continuity equation can be written as, if we have a polarization current, then the continuity equation will be del dot J P instead of J. This is actually the polarization current. This must be equal to, then the continuity equation del dot Jp, which is equal to del dot, putting the value of Jp is equal to partial P divided by partial T. And if I write down further like this, if I change partial T and write down del dot P, and del dot P is actually the divergence of Jp. This is actually equal to rho P, bound current density, with the minus sign as well. Then minus partial divided by partial T and rho B. From the above discussion, we can write down the density. This must be equal to some free density, free charge density plus bound charge density, and this is equal to rho F minus divergence of P, and the current density must be equal to JF plus JB plus JP. This is the free current density, this is the bound current density, this is the polarization current density. If we have all these things in a material, then we must have some bound current density and polarization current density. Then the total current density will be equal to this, and the total charge density will be equal to this. And further, if I write down JB, we know about JB, we already the bound current density del cross M, and plus JP, we know about JP, which is equal to partial P divided by partial T. Using these concept, these things, then the Maxwell's equation can be written like this. The first one, the first equation. And the first equation is the divergence of E, which is equal to rho divided by epsilon naught. But rho, which is equal to this, then this is equal to 1 over epsilon naught and rho F minus divergence of polarization. And this epsilon naught will come to this side, and epsilon naught divergence of E which equal to rho F minus divergence of P. And if I move this part from this side to this side, then epsilon naught divergence of E plus divergence of P, which is equal to rho F. And then if I take the divergence, then I have epsilon naught E plus P, and this is equal to rho F. And this epsilon naught E plus P, this is nothing but this is the displacement current. This thing is the displacement current. And it is denoted by D. Then it means that the divergence of D, which is equal to rho F. So the first equation, when we are using for a material, it will take the form like this: divergence of D, which is equal to rho F. The fourth Maxwell equation, we know the fourth Maxwell equation, divergence of curl of B, which is equal to mu naught J plus mu naught epsilon naught partial E divided by partial T. We know about this. Now J is this one. Putting the value of J from this equation and this, then the curl of B will be equal to mu naught, putting JF plus curl of magnetization, polarization plus mu naught epsilon naught partial E divided by partial T. I want to move this mu naught, this term, to the left side, then del cross B minus mu naught del cross M, which is equal to mu naught JF plus mu naught partial P divided by partial T, and this term as it is. This left hand side I can also write down like B minus mu naught and M, and here if I take out mu naught is common, then JF plus partial P divided by partial T plus epsilon naught partial E divided by partial T, And if I move this term to the left side, then it will go to the denominator del cross, and if I write down like this, then this will cancel out, and jf plus partial p divided by partial t epsilon naught partial e divided by partial t. From these two equations, here this term is denoted by h, the magnetic field and material h, and then this del cross h will be equal to jf plus, if I take the derivative, then this will be equal to p plus epsilon naught e, and p plus epsilon naught e, this is actually the displacement vector d. So it means that del cross H, which is equal to JF plus partial D divided by partial T. And this is the final form of the fourth Maxwell's equation when we are using this for a material. The remaining two equations, the second and third, it has no involvement of current density and charge density, then it will remains the same. It should be noted that no change will occur in divergence of this equation and del cross E, which is equal to minus partial B divided by partial T, because these two equations, there is no charge density and current density. Then the final form of Maxwell equations in matter will be the first one is divergence of displacement current, and this is equal to rho f. The second one is it is del cross E, which is equal to minus partial B divided by partial T. And the third one is a divergence of magnetic field, which is equal to 0. And the fourth term that I have calculated, uh, curl of H, which is equal to JF plus partial D divided by partial T. Uh, these equations can be used whenever we know about the material. If you don't know about the material, which material this is, then we cannot use these equations. These equations can be used whenever we know the nature of a material. If we don't know, if we don't know about the nature of a material, one cannot use these equations, because the reason is because we need the relation between E and D and B and H. If you don't know about the nature of a material, then we cannot use these equations that we have calculated for the Maxwell equation for the material, because we must know about the relation E and D and the relation between B and H. And for example, we have a linear media. If we have a linear media, if we have a linear media, we know about a material that this is a linear medium. And for this, we can write down the polarization as epsilon naught and chi and E. And we also know the magnetization chi m and h. Then d, the displacement vector, is equal to epsilon and E, where epsilon, which is equal to epsilon naught 1 plus chi E. And here h, which is equal to 1 over mu and b, because mu, which is equal to mu naught and 1 plus chi m. So here we must know about h and b. If we know about h and m, then we can use these equation. And similarly, if we know about the displacement vector and electric field, then we can use these Maxwell's equations. And from the last one point is, from the Maxwell's equation, the last term, we have calculated partial d divided by partial t, the displacement current as changing with time. And Maxwell called this JD, the displacement current. So this was the reason that they have used the term.